Hello friends, this video on Electrochemistry part 22 is brought to you by examfear.com. No more fear from exam. It has been seen that, as I already told, the conductivity varies. Right? The conductivity of a solution vary based on concentration. So now we'll understand the pattern of the variation of the conductivity of an electrolyte. We'll talk about the normal conductivity variation, and we'll also talk about the molar conductivity variation. The normal conductivity we just saw is K, and this is lambda for electrolytes. Both for weak and strong electrolytes we'll see that they have little different behaviors. We'll talk about the variation of molar conductivity of electrolyte, and we'll talk about normal conductivity of electrolyte, the variation of both these conductivity. First, let's talk about the electrolyte normal conductivity variation. So here we are talking about the normal conductivity, that is K. So if you see the definition of conductivity of a material is nothing but its conductance when it is 1 meter long and its cross section area is 1 meter square, right? That is my conductivity of this solution, right? In this, please note I'm talking about the electrolyte conductivity variation. So in this case, my current carrier is ions. They are my current carrier. Now if we increase the concentration of ions, obviously what will happen? If you increase the concentration of ions, ion count per unit volume, then the conductivity increases. Right, for a given, let's suppose I have 1 glass of water, you add some 1 teaspoon of NaCl, you measure the conductivity, you add 2 more teaspoons of NaCl, you measure the conductivity. You'll see that the more you add NaCl, that is my common salt, the more conductive is the solution. Why? Because you have more ions. It's pretty straightforward answer, right? But thus you can say that the conductivity is directly proportional to concentration. But there is a catch here. So if you talk about the strong electrolyte and the weak electrolyte, there is a variation. If you see the strong electrolyte, for example, NaCl, is this case, and weak electrolyte, for example, CH3COH. So if you increase the concentration of strong electrolyte, the conductivity increase at a higher rate. But if you increase the concentration of a weak electrolyte, the conductivity increases with a low rate. The question is why? See, this is a good picture actually. This is my CH3COH and this is my CH3CO minus ions, and this is my H plus ions. Here I have my NaCl, this is my Na plus and Cl minus ions. Now just understand that the items on the left, that is my NaCl or CH3COH, they don't conduct current. The current carriers are my ions. So in this case, CH3CO minus, H plus, Na plus, Cl minus, they carry current. That is a very, very basic concept, right? Now, in case of a strong electrolyte, if you increase the concentration of NaCl, let's suppose, NaCl, we know the moment you say NaCl, if you see there's a single arrow here, that means the moment you add NaCl to a water, almost 99% NaCl will dissociate into Na plus and Cl minus ions. Thus, the more you increase NaCl concentration in a electrolyte, you will get more and more Na plus and Cl minus ions. More Na plus and Cl minus ion implies more conductivity. Right? This is pretty okay. The catch is with the weak electrolytes. So the weak electrolytes, if you see, if you have CH3COH minus ions, they are in equilibrium with CH3CO minus and H plus. Thus, if you see, there is an equilibrium sign. What it means is, if you have a dilute solution, then the percentage dissociation is more. Maybe in case of dilute, it is 80% dissociated, or let's suppose 80% is too much, 40%, let me take 10%. In case of concentrated, it will be not even 1%. So there is a difference, right? So if you take a dilute, or maybe it will be more, let's take 40% only. Yeah. Just to understand, these figures may be wrong. Just to understand, I'm taking these figures. If you make very dilute, maybe 100% also. Right? The max is 100%, let's suppose. But if you make it very concentrated, it is then solution will shift on the right. If you make a very dilute solution, the concentration will shift on the solution. The equation, the reaction will move on the right. So if you make a concentrated solution, the reaction moves on the left. Dilute solution, the reaction moves on the right. So what is happening in this case of weak electrolytes? If you're increasing the concentration, concentration of the CH3COH or the weak electrolyte, the concentration of the ions are not increasing at that rate, because the moment you increase the concentration, the reaction is also moving a little bit on the right side. Correct? So thus the effective number of ions here doesn't increase that much. So let's take one scenario. Let's give some better value here. Let's take this to be on dilute, let this be 100%, and on concentrate, let this be 10%. Correct. So if I make a dilute in 1 liter, let's suppose in 1 liter, I have a 1 liter jar, and in that I just put 1 moles of CH3COH. Right? If I put 1 mole of CH3COH, let me see, if I put 1 mole of CH3COH, I get, let's suppose it is 100%, it dissociate. So I get 1 mole of CH3CO minus 1 mole of CH3COH. Correct? Now, if I make it more concentrated, let me make it 10 moles. If I make it 10 moles, so in 10 moles, instead of 100% dissociation, let's suppose dissociation is 50%. 50% of this is, you get 5 moles of this, you get 5 moles of this. Let me make it 100 moles. In 100 moles, let's suppose the dissociation is 20%, because the more you make it concentrated, the dissociation percentage decrease. It becomes 20, and this becomes 20. Let me make it now 1000 moles. And 1000 moles, let me assume this is 5%. So this becomes 50, and this becomes 50. Now you see, you are increasing the concentration from 1 to 1000, but actually if you see, the ion concentration is only increasing from 1 to 50, and that is what I'm showing here. You are increasing the concentration too much, but the ion concentration is directly proportional to my conductivity is increasing less. Right? You see, the increase is less. But in this case of strong electrolyte, if I'm adding 1 moles, I'm getting 1 moles of Na plus and 1 mole Cl minus. If I'm adding 100 moles, I'm getting 100 moles of Na plus, 100 moles of Cl minus. Right? In that case, since it is very strong electrolyte, the moment you put in water, it breaks. So the dissociation is not much dependent on the concentration of the solution. But in case of weak electrolytes, the moment I'm increasing the concentration of the solution, the dissociation is decreasing. Correct? And that's way, if I'm increasing the concentration from 1 to 1000, but actually the conductivity will increase only from 1 to 50. And that's why for the weak electrolyte, the slope is not that steep. Right? The rate of increase of conductivity on adding or increasing the concentration is not as high as we have in case of strong electrolyte. Hope you understand this. Now let's understand the trend for molar conductivity. Now let's see the variation of molar conductivity. We see the molar conductivity is nothing but lambda m is K by C. So variation of K we have seen just now. Correct? Conductivity we have seen. Now if you see, C is what? Concentration. Now concentration is also one of the parameter which we are changing, and that is there in the denominator. So overall what will happen, the value of lambda m will decrease as we increase the concentration. Correct? Because concentration is also one of the parameter. So we have seen for strong electrolyte and weak electrolyte. For strong electrolyte, let me just draw first. This was for the weak electrolyte in the green color, and this was for my strong electrolyte, right? This was strong and this was weak, and this was my K and this was my concentration, right? Now instead of K, I'm talking about K by C, and C is also a parameter here. Now since C is also a parameter, the moment you increase the value of C, the whole value K by C will go down, right, mathematically, and thus instead of getting straight, it will be a little lesser straight. Now if we talk about, this is for the strong electrolyte, example NaCl. But if we talk about a weak electrolyte, it was already less, right? It was going in this, the steep was less. Now if you divide this value by C, and with this C is increasing obviously, then you will see XY is equal to constant kind of graph, right? In the maths you have seen that, right? So if you see this value, because this value if you see is almost constant, I think this is almost constant, almost constant, right? We saw the slope was almost constant, and this X and Y we are changing. It will give you this kind of graph. So this is mathematically, you will see lots of textbook has different explanation, but if you think from experiment perspective, right, molar conductivity and conductivity is just the name you have given, but actually the mechanism going inside is same, right? The weak electrolytes, the moment you increase concentration, it dissociates less. But for strong electrolytes, even if you increase concentration, it dissociates almost completely, and that's the reason why we have difference in the graph, right? For the normal conductivity, the strong electrolytes, the step is pretty high, right? The increase in concentration leads to a very high increase in conductivity, but for weak electrolyte, increase in concentration leads to a very minor increase in conductivity. If you talk about the molar conductivity, the same value you just divide by C, mathematical representation. So there you will see, since there was a steep graph, the moment you divide, you get this kind of graph, and since this was almost constant, you get XY is equal to constant type of graph in this case of weak electrolyte. Correct? One thing to note here is, now if this concentration is becoming almost zero, then this graph goes in this direction, something like this, because that's the graph for XY is equal to constant. Now at these values, when concentration almost approach zero, then in that case my molar conductivity is given a new name, and that is called limit molar conductivity. It has a very great importance, and that has a special symbol E with two dots M naught. Because at this point, if you see, the conductivity shoots up like anything. The molar conductivity shoots up like anything, right? It becomes very high. And at such a dilute level, it is very difficult to find the conductivity using this kind of setup. Because, see, another day what we do is we use this Wheatstone bridge, right? We use this 4 resistors, we use this Wheatstone bridge, right? And then we use some voltmeter here, and we pass some AC source of current. Now, if I am making it very, very dilute, if I am making it very, very dilute solution, almost zero, then in that case, this is the AC power. If I am making it a very, very dilute solution, in that case, what will happen is, this whole electrolyte won't even conduct electricity. It will conduct at a very, very small level, right? The resistance, the bulb will glow a very, very minor level. So at that point, it is very, very difficult to measure the conductivity, right? Because its values are very high. So it is very difficult to calculate the values of conductivity at that point, and thus we need a different law for this. And we'll see that we have Colroche law, who has proposed a law to find the conductivity of strong and weak electrolytes at low concentration. In fact, for weak electrolytes at low concentration. Correct. In fact, thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.